Hey there, Calc 3 folks, back here with the last video lecture in my semester here, where we're going to take note quickly here on the divergence theorem, right? What the divergence theorem is, it is a calculation of the outward flux on a surface involving a triple integral calculation when it's the case that our surface is what we call a closed surface, where it defines a simple closed solid or region D that is a solid in three-dimensional space. All right? And if S is a surface, a closed surface defining a solid region in R3, the divergence theorem can be used to calculate the outward flux of that field across the given surface, right? And this is again done by integrating what we say is the divergence of F bar, right? The divergence of the field over that solid. And it's done using a triple integral known as a solid integral. All right, we've looked at linear integrals, we've looked at surface integrals, and now we're looking at integrals over solids, or solid integration. Anytime you perform a triple integral, you're performing what's known as a solid integral. Now here's what the divergence theorem does state, right? It does assume that S is a simple closed surface defining some solid region D in three-dimensional space. All of this within some vector field F bar, all right? Then the outward flux of F bar across S, we might say here, across S, is given by what we're familiar with as that calculation for the surface integration for outward flux across a surface, right? This surface integral seen here, where to calculate this double integral over the surface, we're actually going to perform this calculation here, which is going to be a triple integral over that solid region of D, all performed with respect to the volume of D for this quantity here as an integrand, the del operator dotted with our field function F bar. Where if you take note, we learned about this del operator dotted with F bar back at the beginning, looking at vector fields, where this is known as the divergence of the field, right? And what this integral operator is doing is we are integrating the divergence across this entire solid, right? Note this triple integral is known as a solid integration, right? Integration across some solid D, where in this case, what we notice is that del dotted with F bar is the divergence of F. So what this calculation is doing is integrating that divergence of F across the entire solid, right? With this result being what we call the outward flux of the solid, well, the outward flux of F bar across the solid's boundary, which is defined by our surface S. Now, again, how this calculation is performed, folks, is you will be presented with a surface flux calculation, this outward flux calculation, where you can calculate that surface integral using a triple integral of the what would be divergence of the field. You can set it up as a triple integral if that surface is defining some specific solid in the space, a solid that you can define using triple integration. Right? A solid D that is definable. All right? If we consider a case here, right? We might consider the outward flux here of F bar given by the vector field x, comma, negative 2y, comma, 3z over the surface of the sphere. Here we're going to be working with a surface given by the shape of a sphere described by this set of x, y, z coordinates. It's all the x, y, z coordinates where x squared plus y squared plus z squared are all equal to the value of 6. Right? This is a sphere centered at the origin in three-dimensional space with a radius given by the square root of 6. And because we are looking here at a solid region of D, right, being encompassed by this surface, what we can do is we can approach this surface integral calculation using divergence theorem. And what we're going to do is not only approach it using divergence theorem, if we take note of the shape of the sphere, right, and if I actually bring into play the illustration of this case, because we are going to be integrating a field across some surface that is spherical, we might be able to approach this triple integration calculation within the context of the spherical coordinate system. Right? And what you can see here in this illustration is our surface, that sphere, with a radius given by the square root of 3, which is somewhere between 2 and 3 in value, right? For the sphere centered at the origin, where here we have this field moving through this sphere. Right? You can see the upper half is moving up and out, kind of twirling here to the right, whereas the bottom is kind of moving down and out, kind of twirling here to the right. And the closer we get to the equator, we still have outward flux. We can see that here along the boundary, but it becomes more of a circling around the, what we might say is the equator of this sphere. Right? Where if we set up the calculation for this outward flux caused by this field, right, I do believe we're going to see a positive outward flux based upon the illustration. Now, one thing we note is in the case of f of bar given by x comma y comma z equal to x comma negative 2y comma 3z, the divergence of f bar, right, remember what the divergence is, it is just the partial of the first term in terms of x added to the partial of the second term in terms of y, and the partial of the third term of our vector field in terms of z, which is just going to be 1 plus negative 2 plus 3 in value. Or if we add that up, that does add up to positive 2 in value. All right? We do have a positive constant divergence across this entire field. All right? As for the solid, we can define the solid using the definition of a sphere given in the rectangular system, or we can approach it here in the spherical context, where in the spherical context, we get a nice, clean description of this sphere, right? We get boundaries on the parameters of this sphere, right, that are between constant bounds. Theta between the bounds from 0 to 2 pi. Notice the sphere forms for angle measurements with the positive x-axis that form all the way around, starting at 0 all the way around to 2 pi for one complete revolution around the equator of this sphere, right? The sphere forms for angle measurements with the North Pole, right, phi values that start at phi equal to 0 at the North Pole and continue all the way down and around to the South Pole, which would be where phi is equal to pi, right? So that is across these bounds of phi from 0 to pi. And the solid forms for distances from the origin, rho, that start at the center of the sphere and continue all the way out to that outer edge, which is from 0 all the way out to the square root of 6. Right? These bounds on our spherical parameters in our description of D are nice constant bounds. Whereas if I try to define this sphere in the rectangular coordinate system in order to set up a triple integral, that would be a rather cumbersome calculation. Here, things are going to be simplified nicely. Right? In terms of that triple integral, right, one thing we do want to note is if we're going to approach it in the spherical context, we're going to have to incorporate that Jacobian multiplier, that rho squared sine phi value. And what you will notice here is we do have set up what our definition defines as this triple integral by divergence theorem, where we do know what the divergence of f bar is. We did calculate to be the constant value of 2, but because we are going to approach this within the context of region D being defined by the spherical coordinate system, right, We are going to integrate d rho, d phi, d theta, where we need to incorporate that extra Jacobian multiplier into our integrand, which would be given by rho squared sine phi. All right? And as you note across these bounds from rho, phi, and theta, we see these bounds of integration from 0 to the square root of 6, from 0 to pi, and 0 to 2 pi on the outermost bound. Where if I integrate this first with respect to rho, it's going to bump up to 3, divide by 3. It's going to become 2/3 as a constant multiple. We might bring that out in front. We're going to evaluate this from 0 to the square root of 6, which is really just 6 root 6, if you think about root 6 to the 3rd power. I do believe that is the next result. Here we have 2/3 then times the double integral for what's going to be rho cubed sine phi, evaluated from 0 to root 6, d phi d theta, which does just produce 2/3, this double integral from 0 to 2 pi, 0 to, how did I get phi up there? That should say pi, right? For 6 root 6 sine phi, right? Where the cube root of phi, or sorry, the cube root of rho, evaluated from 0 to the square root of 6, is actually going to be 6 root 6 at its uppermost bound. At 0, it zeroes everything away. All right. So now if I integrate this statement with respect to the sine of phi, that's going to be negative 6 root 6 cosine phi. All right. Which is, we might leave the negative cosine phi inside the brackets, bring the 6 root 6 out and make that 12 root 6 over 3, or 4 root 6 on the outside. And have on the inside negative cosine phi for our integrand, where that negative cosine phi is now going to be evaluated across those bounds from 0 to pi. At pi, cosine of pi is -1, so the opposite of that is positive. We see that positive 1. And then we subtract the cosine of phi at 0. The cosine of 0 is 1, so we're going to subtract. This is going to produce -1, so we subtract away -1 in value, which is like adding 1. All right, that's 1 plus 1 inside there. That is an integrand now that is producing the value of 2. So we might bring the 2 out and make this 8 root 6, the integral from 0 to 2 pi for just d theta, which would bring in just theta evaluated from 2 pi, or 0 to 2 pi. All right. We can see that setting itself up here, and actually I missed that theta there, right? Where we're going to be integrating 2. 2 could come out as 8 root 6, and the integral of what remains would just be theta from 0 to 2 pi. At 0 it is 0, but at 2 pi it is 2 pi, and 2 pi times 8 root 6 becomes 16 root 6 pi. And what this calculation is here, folks, is the measurement for the outward flux of this vector field across the spherical surface. There is a positive outward flux, right? More of the field is passing through the surface in an outward motion than is moving into the surface. More of the field is diverging from the surface than is moving into the surface in terms of the fluctuation across the surface, right? And remember, what flux does measure is that amount of the field that's moving orthogonal to the surface, right? And the total amount of field that's moving orthogonal to the surface is 16 root 6 pi units in measurement. That is the flux of this field across this surface. All right? And you can see here, folks, we are just setting up a triple integral calculation for the description of our solid. We are preparing the divergence of our given function f. Now, if this had yielded some argument in terms of x, y, or z, I would have to translate those values in my integrand to statements involving rho, phi, and theta from what my understanding would be back in the conversion from rectangular to the spherical coordinate system, right? Or if I was to approach this in the polar system, I would have to do respective transformations. Or if I stayed in the rectangular system, I would just use this argument involving x, y, and z. And then the bounds on that integration, right, are just the bounds on how we define our solid D. Here we defined everything in the spherical context. So my bounds on D are defined in the spherical context and integrated with respect to the order d rho, d phi, d theta, where I do, because of the conversion into the spherical context, have to make this Jacobian transformation of the integrand, take this rho squared sine phi and incorporate it into this factor along with the divergence of f, right, along with that value of 2. So we get 2 rho squared sine phi as our initial integral. All right. As with triple integrals back in multiple integration, if you incorporate or if you transform from one coordinate system to another, you do have to incorporate that Jacobian multiplier. All right. And we do see that happening in this calculation seen here. All right. Folks, that is it for the semester, divergence theorem. All right. It's not a lot going on there. It is basically saying here's this outward flux that you've learned about calculating back in surface integrals, where if that surface is defining a three-dimensional solid, you can actually perform that outward flux calculation using triple integration of what would be the divergence of the field inside that solid, right? The divergence of the field within a solid describes the fluctuation across the boundaries on that solid, right? That is what we see being defined out here in the divergence theorem, right? I hope this all helps, folks. I hope you're doing well. I hope the semester ends good for you. So, folks, again, I hope you're hanging in there. I hope you're doing well. The semester, I guess, is very close to being over here. This is my last video lecture here in calculus for you. My plan in the fall is to teach the evening section of differential equations. If you're at all interested, you might want to consider getting signed up into that course, because certainly if the enrollment doesn't get high enough, that may not make next semester, right? So I'm just out there trying to spread the word. And then likewise, there are likely some surveys that you're seeing over the next couple of days come through your emails. I want you, hopefully you can fill out those surveys and give some constructive criticism with respect to this course, with respect to just having to learn remotely here this last few weeks. I think there's a survey the school's sending out with respect to the remote learning situation that you've been involved in. There's going to be the course evaluation coming out there. Please give me some good constructive criticism there. And then likewise, I might even have a survey I put up on Blackboard for you folks. I'm up for promotion next year to full professorship, and I do need some student feedback there when I petition for my promotion. And I would appreciate any feedback you could happen to share. So you might see that popping up on Blackboard over the next couple of days, and please fill all that out when you get a chance. It's one of the ways that you kind of help motivate change on campus, folks, whether you think about it or not, or realize it or not, is that those surveys that you are asked to do are by the administration and for almost anything dealing with campus is a way of kind of motivating change and facilitating some change on campus, especially if there's a lot to be said there. So, again, I hope you're doing well. I hope you're hanging in there. If you need anything, you know how to get a hold of me. But this is it, folks. We're right here at the end. So, I'll be looking for your tests soon enough, and we got the final next week. If you're at all interested, I'll be working on grades and getting all that out as quick as I can here. But with that said, see you next time.